So welcome to the second last lecture. We're going to have, and this is something which I wrote to you, there is a small error in the time planner and the schedule because next week doesn't pop up. So next Monday is the last lecture. And we do have labs next week as well. So this week and next week, I mean, the focus will mainly be on project number 3, obviously. And the weeks thereafter, which are essentially in the exam week, from experience, it's very few actually people who show up. But if you have questions, I mean, just feel free to swing by. So we will not have the labs open in the weeks which start with December, I think it's December the 3rd and all. Okay, so we had it last year, and I think during the 2 weeks we had it open. I mean, there was only one who came. So then we decided we won't keep them open. But we will have labs till the end of next week. Okay, so the topic today is to try to continue the discussion of recurrent neural networks. And for many of you, this can be a very popular method to use in the final project, together with, let's say, a standard neural network. If you're studying time series, this is actually one of the standard methods which are being used. If you're looking at natural language processing, you can train a network on words which have been read in before, and then you can let the network make a prediction for how this phrase would continue. So for natural language processing, biological time series, I mean, time series in physics, geophysics, whatever, this is a very, very popular set of methods. And I want to demystify some of the inputs. We are going to look at the code examples. And for the project number 3, as we also discussed, I mean, when it comes to convolutional neural networks, autoencoders, which will be our final topic, and recurrent neural networks, we normally recommend that you use software libraries like PyTorch and TensorFlow. And in the slides for this week and the week before and also next week, you will find examples on how you can implement recurrent neural networks, convolutional neural networks using PyTorch or TensorFlow. So it's up to you to choose the one which you find the easiest to use. Okay? So for the projects, if you want to use these methods, we would normally recommend using these libraries because it would take quite a lot of time to write your own recurrent neural network code or a CNN code. So we do have a course which is called Physics 5429, Advanced Machine Learning, and there we can have as a 1 semester project to actually write an RNN or a CNN code. So for these 3-4 weeks which we have left, I do not recommend writing your own code. Okay, any questions about this? Good. So what I wanted to do now is to give you a quick reminder of the setup of a simple recurrent neural network. And then we're going to revisit some of the topics which we discussed last week. We are going to dive into examples. And then due to the fact that we have the problems with exploding gradients, et cetera, and the problem to really simulate long-term time dependencies, then we are going to introduce another way of setting up a recurrent neural network, which is called a long short-term memory. That's one of the possible approaches. And we will go through the basics, how you set it up, and what it essentially means so that you get an intuition about what you're actually doing when you set up a long short-term memory recurrent neural network. But the first thing we are going to do is to look at how we can write our own code for a recurrent neural network, a simple one. So I'm going to switch back to the whiteboard and quickly remind you of the basics of a recurrent neural network, a simple one. So let's just do that before we move on. And you will see many of the, in the lectures here, there are many reading suggestions, but the main ones are actually chapter 10 of Goodfellow et al., which is a good read for RNNs. And then in Rashka's textbook, the other one which we normally recommend, then chapter 15 contains actually many nice discussions on how to implement them in PyTorch. So the programs you will find in the lecture notes are inspired in PyTorch by Rashka's text, and also the figures which you will find are figures which I have borrowed from Rashka. So hopefully that guides a little bit the reading. And then there are TensorFlow examples if you're interested. And then we also will start looking at autoencoders, which we will continue with next week before we wrap up everything. Okay, so let's switch back to the whiteboard and take a quick look at the basics of a recurrent neural network. So what we said last time is that we have something which we call recurrent units. So these units, that is where we have the hidden layers. These units can be a plain, simple neural network with just one layer, or it could be a convolutional neural network. It could be an autoencoder or more complex networks. But keep in mind that at the heart of everything which we do have a standard neural network. That is pretty common. So let's make this drawing again, which we had last time. So we would start with some initializations, and we call this H0. This feeds in to a new hidden layer, which is we call H1. At this stage, we could have some input X1. So it could be a mechanical force which you apply on the system, and that produces an impact on your system. You have, in this H1, you train a model on the data which you're feeding in, which comes from a previous time step, H0. So the hidden layers are connected. So every such H bubble, which you see here, is called a recurrent unit. This is a variable which you need to define when you use either PyTorch or TensorFlow. So you have to specify the number of units which you're setting up. So in this particular case, what you would do then is to produce an output, and we label this output Y1. And this feeds into a cost function, which we label as L1. And in this case, what we have is that this is now tuned against a target value, T1. So T1 is not time, but it is the target value. So this could be you make a measurement of the positions of a bike. So at the position X1, you measure, for instance, the velocity of the car, and then, or the bike. Then at the position X2, you measure the velocity, etc., etc. And then you want to make a model which reproduces the velocities. So the velocity here, which you measure, so this could be an actual measurement. Or, as you will see in one of the examples later, I have combined a differential equation solver with a recurrent neural network. And I use the differential equation solver at every time step. It gives me velocities and positions. And then I can train a recurrent neural network against the output of a numerical simulator. That is a very common situation because sometimes these numerical simulators are time expensive and they are time consuming. And that means that you would like to simplify things. So you have some data which you have produced up to a given time. That is your training data. And then you train a recurrent neural network on that. And then you use a network to extrapolate. And hopefully, you're hoping for, the network does well. And it is a good predictor when you extrapolate. And it is cheaper from a computational point of view than you calling your fancy differential equation solver. So these are the kind of compromises which you have to strike. In other cases, you may have experimental observations, and these observations stop at a certain time. And then you want to make a prediction for later times. So what we had then was that this recurrent node, or unit, as it's often called, this feeds into the next one. We may have a new input. So this could be us measuring the velocity at a position X2. Our model produces an output, which we call Y2. This goes into the loss function here, L2, and that has a target value, which could be our measurement, so T for target. And this continues to the next one, etc., etc. And this can just go on till the final unit, H of n. And we have a final input here. So this could be us feeding something into the system, which then changes the state of the system. We then train data, and then we have a new output, yn. This feeds into a new loss function, ln. And this has an observation which we want to reproduce. So these guys, which you see here, they are normally called the recurrent units. So that's a kind of naming which you will use as a variable when you call or you use PyTorch or let's say TensorFlow. Now, the training here, it takes place through weights, which we call WHH, so they connect the hidden layers. We have weights and obviously also biases, which connect the hidden layer with the input X. So that gives us new variables to train. And then we have an output layer, which is Y1 and Y2, etc. And that gives us a new set of variables, which we have to train. And then the cost function, the total one, C, is just the function of all these individual from I = 1 up to n. And then we have these L's of yi of t of I. And these are the functions which are then optimized with respect to the weights and biases which we have here. So these will be our parameters to be trained. Now, as you quickly see, if we train these for all the recurrent units, this is going to be expensive from a computational point of view, both with respect to number of floats we employ and also in terms of the memory we need to use. So it's pretty common to train these parameters in the W's for a certain set of recurrent units, and then they're used for all the remaining ones. So I'm going to bring back some of the things which we had to train and how this is done. So in principle, what we have is that we have some input here, which feeds into this function. So this HI here, or H1, as we called it here, receives an input from the previous layer. It receives an input from these input variables. It then produces an output, which then is fed into the cost function. And everything is trained by back propagation. So you have a feed-forward pass where you go through the whole network in a very sequential way. And then you have a back propagation path. And this is called back propagation in time, because you do it for every single time step. But in general, you don't do that because this becomes expensive. And last week, we discussed the problem with the exploding gradients, which is a very common problem. And we saw how these could explode by looking at the simple mathematics of the weights which connect each single hidden recurrent unit. So keep in mind that each one of these recurrent units, this could, for instance, be a convolutional neural network if you want to. It could be something which could be a deep neural network if you want to. And these are parameters which you can define in the setup. Okay, any questions? So this is just quickly to remind ourselves what we did last week. And I'm going to bring back the slides here because today is going to be a slides day, unfortunately. So if we now look at a recurrent neural network, in basically what we have is this is a compact way of setting it up. When we unfold it, we have some inputs, and often you would start everything with random variables for these variables. And these feeds through the network. So there's a connection here from one hidden layer to the next one. And this connection is the one which often becomes time consuming and makes it sometimes difficult to parallelize because you depend on the previous variable. And we mentioned last time a way to circumvent it. So these images which you see here, actually taken from Rashka's textbook. And as you can see, you can have a recurrent unit which contains more than just one single layer. So you can actually make this as complicated as you want. And there are tons of examples which you can actually get. So if we scroll down here a little bit, another feature which is interesting for us, and that depends on the type of output data which you have. So you can have, suppose you just want to measure one final result. You could have the one up to the left where you have many to one. So you could think of you having different inputs at different time steps, but then you have only one output. You can have one to many, so you can have one type of input. That means that if you look back at that figure which we draw, the axis which you have, there could be only one. So you have a measurement of the positions at a given time, and then you don't make any other measurements. But then at every time step, you're measuring the velocity, just to give you an example. So these are typical settings which give you, as a user of RNNs, quite a lot of flexibility in the type of problems you can attack. Any questions so far? Okay, so let's just proceed a little bit. So this is roughly what we did last time. And you can see now when you unfold it, you get to see the kind of weight matrices in a single unit which you need to fit. So you have these weights which connect the input with the hidden. The hiddens are connected by these weights. And then the hiddens are connected to the output layer with its own weights. And this result obviously feeds into a cost function at a given time step, which then receives an input if you make a measurement. If you're dealing with one many to one, then the final measurement would be here, where you would compare with some kind of target value. And when you set it up, this is just a quick reminder from what we did last time. So you would have, if you look at this one, you would have an input which comes from the axis multiplied with the weights, as before. We have an input which comes from the previous hidden layer, which then multiplies with the output from the previous hidden layer, plus these biases. Then we have an activation, which could be a tanh. This is something you need to specify when you're setting up the codes. You have a new one when you proceed here. So you have the output here, which feeds in to the output layer. So that means that there is a WYH here, which is multiplied with the output. So the output from the hidden or the recurrent unit feeds into the output layer at a given time. So I'm using time as an example. It doesn't need to be time. So you will see later that we can actually slice up the data so it looks like a time sequence. But you can think of time now as a kind of variable which could apply to time series, but also to something else. When you do this, you see now the functions you need to train, and these are also the gradients which we need to train. So we need to set up these different guys, and then we need to roll back in time. And the typical way of by the way which this is done is actually by back propagation in time, which we discussed last time. So a typical task is actually what we call a character level classification, which has been used for. So you would feed a name, a sequence of characters, and one character at a time, and classify its language of origin. That's a very standard applications of these methods. And at each time step, the RNN outputs a hidden state. We use the final hidden state to predict the class of the entire sequence. So that would be a typical way of applying this to natural language processing. So my background comes mainly from the natural sciences, and the type of applications I've been using has been to make predictions, use the neural networks, fit them to data from a differential equation solver, just to give you an example, and then use a recurrent neural network to make predictions, because often the codes I have for producing results are time consuming. And then I want to save CPU cycles by predicting with a model which has been trained on the data. Now, there's something I wanted to say a little bit about. What you will find here is a simple case where we use TensorFlow. And in this particular case, what I'm setting up is an input size of dimension 10. I have a hidden size, so this is the number of recurrent units. So keep in mind that the recurrent units are these different guys which you see here. And then what I'm also defining is something here which I call sequence length. So in this case, I'm doing a binary classification case. I have a batch size of 16. I have now something which I call a sequence length. What does a sequence length mean? Has any one of you heard of that before? So let me try to show you by switching back to the whiteboard what a sequence length is. This is something which is used widely when we are dealing with recurrent neural networks. So let's just jump back to the whiteboard before we proceed and look at that code example here. Because this is a variable which you typically feed into a recurrent neural network. Now, so what we are going to do now is something which we are going to introduce, which is called a sliding window in the kind of literature. So it means that you convert a long time series into many overlapping short sequences. And each of which becomes one training sample for a recurrent neural network. And this is actually one of the most important pre-processing steps in sequence modeling. So if you now take a given time series, so typically the way you would have the data is something like this. So I'm going to introduce something which is a sliding window. So this is another name for it, of length . And you saw that variable which I called it for sequence length. So I'm defining so you don't need to call it sequence length if you don't want to write these long words. You could just write sec length or something like that, but you need to specify that. So the whole idea now is that when you have this, suppose you have a time series. Given a time series, and you have something which runs like, let's say, x0, x1, x2, up to some xt for the t final time. What you do then, when you define this sequence length, suppose I define sequence length equal to 3. What I'm doing then is to set up a kind of sliding window where every block contains 3 points. So what I'm doing now is to set up a block like this, x0, x1, x2. Then I have a new block which starts with x1, x2, and x3. And now you see the pattern here because the next one is x2, x3, and x4, and etc. So this kind of each window then, which you have here, so each one of these is called a window. So each window or sliding window is an input sequence for a recurrent neural network. And what you're seeing now is that when you do the training, it means that the next sequence contains data from the previous sequence. In that way, you keep information about the memory from previous time steps. So instead of you going from x0 to x1, x2, etc., and just have a simple sequence equal to 1, you're now bringing in, or you're forcing in some memory elements so that The second window here is trained with a value from the previous one, which is also contained into the next one, etc., etc. So the whole idea here is actually that, so within each window is an input sequence to a recurrent neural network. Because if you're doing one-step predictions, then your input window is just something which contains, so if you have a one-step prediction, then your window would simply contain this part here. But then with a sliding window, what you can do then is actually that your data is, you split up the training into many, many subsequent windows. And the hope then is that this can take into account correlations in a better way. Let me just bring up one small thing. There was an argument here which I need to remind myself of. So one of the reasons why you have this sliding window is that reshapes the data. So in a certain sense, you actually have much more sequence data which you do the training on. And the hope then is that this takes into account in a better way correlations among the data, and that it gives you a better, a better way of finding the time correlations which may exist from, let's say, X2 to X3, X3 to X4, etc., etc. So the sliding window is one of the parameters which you typically would define, and it normally improves the quality of the results. So let's go back to the code here and look at a very simple way by which you can set up your first recurrent neural network. So in this particular case, we're just setting up the data here. I'm defining a so-called sequence length. And then I'm using Keras, and the function you would call then is a simple RNN. You define the number of recurrent units. I have an activation function, which is tanh, and I set up the input shapes, and this defines the outputs. So I have a dense class. I define the optimizers, in this case, Adam, with a learning rate 10 to the minus 3. And since I want to do a classification, this is actually the categorical cross entropy with two classes here. And the metrics is the accuracy. And that's a very simple model which you can set up. And when I want to train here, I just do a simple case with 5 epochs. This is my model fit. It has X and Y, the batch sizes, and then it just makes the training and makes a prediction here. And these are the kind of predictions which it's making, which is not very impressive. But here I define the sequence length as the number of time steps in each input sequence, which is fed into a recurrent neural network. And it represents how many time points we provide at once. It's the number of ordered observations in each sample or data set. And then we have a return sequence, which is false, which makes the output only, output only the last hidden state. You can actually, if you want to, you can output at every time step. So if you're only interested in the output of the final step, this is one way by which you could do many to just one. If you want to spit out the solution of a differential equation which have been fitting at every time step, then you would have to take away this false option. And you will see examples of that a little bit later here. And then there is a corresponding example with PyTorch, which I'm not going to cover. You can just take a look at it. It's essentially the same. Now, the backpropagation through time is the one we discussed last time. And the typical thing which is being used is actually to use a truncated backpropagation. So instead of backpropagating through all t time steps, you backpropagate through a fixed window of length tau. And this approximates the full gradient and reduces computation. And then concretely what you do is you compute the gradients up to tau, and then treat gradients beyond that as 0. So there's no training. You just use the same weights which you had up to that given time step. And this typically allows learning short-term patterns efficiently. Then you have gradient clipping, which we discussed last week, which is a simple test which is normally implemented. And you will find that as an input option to a recurrent neural network, where you can simply say that if the gradient grows beyond a certain value, then you clip it. And then you put it down to a smaller value. And we discussed the recipe last time. And normally these recipes, these kind of rules, these techniques actually help to stabilize the training. However, one of the problems with the simple recurrent neural network is that it normally has problems in accounting for what we normally call long and short-term memories. And this is why people often use what's called LSTMs or GRUs, which we will come back to. And I will show you also how you can use that in a simple way if you want to train a recurrent neural network on your data, if time series is what you want to do in project number 3. So as I said, vanishing gradients, these simple RNNs have a fundamental difficulty learning long-term dependencies due to the gradients, as we discussed last week. Then, without these gates, the RNNs may struggle with the task requiring remembering far back inputs, and training can be slow as it is very, very sequential. And the alternatives, which we'll come back to later, are the typical LSTMs or these GRUs. And we will discuss the LSTMs, or nowadays, and this is something which we don't cover here in this course, but we cover that in the advanced course. These are transformers. And I guess everybody here is familiar, have heard about transformers, right? So transformers, reinforcement learning, and topics like that, these are topics which we teach in a more advanced course. So the whole idea here is to give you the feeling of what a deep learning machinery means, starting with neural networks, and then going through CNNs, RNNs, and autoencoders, which are the standard deep learning methods. Now, obviously nowadays, since this is a field which moves very, very swiftly, there is a lot of progress and new methods, new algorithms popping up almost on a daily basis. So sometimes you may ask, how should I keep up with what is happening? Hopefully, this course gives you the basic input so that you can jump into the methods which are being developed nowadays. Because many of these methods actually have at their heart a neural network. So having demystified that and understood what it means as a universal approximator is a fundamental input ingredient for more advanced methods. So I hope you can be a little bit patient and bear with me, since I don't discuss transformers and more advanced methods like reinforcement learning and how to use different agents, etc., etc. It's also a 10-credit course, which also has to has to make some limitations. Now, what I've done here is to include 2 examples which we discussed last week, where I'm simply producing a sine function. So I'm setting up a sine between 0 and 0 and 100, as you can see here. And I set up 500 values, and I'm going to use the first 80%, which means the 41st ones, as training data. And in this specific case, you will also see that they have defined this sequential length to be 20. So that means that the first sliding window will go from x0 to x19. And then the next one will start with x1 and goes to x20, etc., etc. So these are that's the sequential length. And as you can see, this becomes a hyperparameter which you set up in the beginning of your calculations. And here you can now see the way I append the data. And take a look at this, because now I'm setting up the data. So I have this sequential length. So it's a sequence of length, sequential length. and that contains the next value to predict. And this is a common trick which is being used, as we discussed, these sliding windows. And this becomes a parameter you can play around with. What is the best length of the sequence of input data which you have and output data? And then we set up in the training size, which is the first 80% of the data, so it's an 80-20 split. And then we have a simple model here where we set up we have actually defined the number of recurrent units. This will be done a little bit later. So we define it here, 16, as you can see. And this is the number of recurrent units. And each one has a layer, one hidden layer. You can actually specify more layers if you want to. Okay? So this is typically the way you would set up the parameters for running the calculations. So my simple RNN is this one. This is actually a neural network, as you can see. And then it has an output, which is just linear, which you also have implemented in project 1, because in this case, we're just fitting a sine function. So it's just the output which we are looking at in a linear way. It contains a training set, and here we set up the number of epochs. We define batches. We look at the backward propagation in time. We set up, we print epochs only in units of 10. And this is typically the loss function which we have. We evaluate the model. We have a convergence criterion which we put up. And this is the final result where you can now see the prediction which we are making, the actual, and this is the prediction. So there's a loss function, which if you can live with that, it's not so bad. And this is the prediction made compared with the actual value. If you do this with TensorFlow, you would see much of the same philosophy. This is just us setting up the data. We split it in train and test. This is done by ourselves, so we're not using the standard scikit-learn. The thing which I like with, I actually haven't found that option in PyTorch. If somebody finds that, please let me know. But TensorFlow has a nice way to summarize the model with all the parameters you're fitting. And in this case, as I said again, you have 16 recurrent nodes. It sets up the number of parameters which you're training, and you're training it in a dense standard model. And when you do the training, you can see again, you can just print out the number of epochs you're doing and the training here. And then if you scroll down, you will see that you are making a prediction here, which is similar to the one which PyTorch gave you. So these are typical examples of how you would implement a simple recurrent neural network where you specify the number of units and you also specify what each recurrent unit is going to look like. And there are some default values. You can also specify how many nodes you want to have, let's say, in just one of the hidden layers in the recurrent unit. Now, we have a series of lectures which we actually have been using for the more advanced course where we actually can build a recurrent neural network. And if you want to look at that, I mean, if you are tempted to write your own code later or in connection with that advanced course on machine learning, there is an example on here actually where you connect the mathematics of a recurrent neural network with the actual implementation and you writing a recurrent neural network code. So feel free to take a look at that one. Now, the thing which we are going to look at now is something which is called long short-term memory. And I'm going to step you through this not in real depth, but I want to have you with me so that you have an intuition of what is going on. And because in this course, we're actually just going to use the LSTM as a way to improve both the quality of the results, but also to get a better hold of long-term memory correlations. And it uses a memory cell, so keep this in mind, for long-range time dependency or dependencies. And it also avoids, so it was actually introduced to avoid the vanishing gradient problem. So instead of doing gradient clipping and treating vanishing gradients, these were actually introduced in the end of, I think, the 90s, 97. That was because these methods are pretty old. But what we normally call the deep learning revolution is something which kicked in roughly around 2010. And this has essentially to do with a famous paper by the guy who gave a seminar last week, Ben Zhou, where Ben Zhou actually showed that the way to initialize a standard neural network with random weights and also using a sigmoid activation function could actually lead to problems with vanishing gradients or exploding gradients. And that had actually kept the whole machinery in a way, in a kind of lock, in the sense that people had problems in training properly. I mean, the universal approximation theorem, when that came in 89 with revisions in 91, that gave a huge boost to the whole field. But then it took something like almost 2 decades before the field really took off. So we normally say that the deep learning revolution is something which really kicked in around 2010, in particular with CNNs. That was the method which, when it comes to image recognition, really started what we call the deep learning revolution. And Ben Zhou, who some of you probably listened to last week, is one of the people who actually started everything. So how many of you got the possibility to listen to Ben Zhou last time? Yeah, some of you. Good. Good. I think it's very nice if we can meet people like that, because we've been using the textbook every week, right? And I'm giving you reading recommendations from Ben Zhou's book with Goodfellow and Colville. So the typical information here, I'm going to set it up a little bit below here. So there are some details, and there's something which we are going, and you will see that from the graphs which come. There's something we will call the input gate, the forget gate, and the output gate. And there's also something which is called a cell state, which you can think of as the keeper of the long-term memory. And then there's a hidden state, which can be thought of as the short-term memory keeper. So it tries to strike a balance between long-term memory and short-term memory. So each of these gates contains one, a memory cell, and 3 gates. One, the forget gate, there's an input gate, and there's an output that control the flow of information. So the forget gate chooses which information to erase from the previous cell state. So the previous cell state, if you now look at the figure which comes down here, so there is a basic sketch which you will also find in Rashka's textbook of an LSTM cell. So you can now think of these recurrent units as being replaced by these cells. And what you have then is a memory cell, which then in a way, when activated or not, tells you which memory to keep track of. So the hope is that the C takes care of the long-term memory. And then you have an H of T-1, which is the one, if you think back to the recurrent neural network, is the one which keeps the short-term memory, the memory from the previous recurrent unit. So you can think of these cells here as something which replaces, if we now go back again, a little bit up here, if we go back to the units here, you would have recurrent units, and every one of these is divided by a given time. This is time T-1, time T, and this contains then what we call a short-term memory information, if you're thinking of these as short time steps. That means that if you are far away here, you may not be able to catch properly long-term correlations or long-term time correlations. So the hope here is that with these LSTM cells, which then would replace these guys here, you can then keep track of both long-term memory and short-term memory. This sounds like a recipe against Alzheimer. I hope nobody of you has a relative or parent which suffers from Alzheimer, because then typically when you suffer from dementia, that's when your short-term memory really starts vanishing. But your long-term memory is there. So you may remember things from your childhood perfectly well. So the way you would set this up, so you have this memory cell and the forget and the input, which decides which new information to add to the cell state. And this one controls which parts of the cell state become the output H of I, which is then fed into the next cell. So there are parameters which we need to update. So this forget gate has its own weights. It receives an input from the previous cell. There's a bias. This input gate depends also on what comes in previously. And then we have the memory cell, the long-term memory, or the cell state update, which is then also given by a activation function, which often is taken as a tanh function. And then we produce also an output, H of T, and then through this output gate here. And all of this is something which you would set up through a typical gate like this. And after the break, we are going to look at this from a top-down point of view. So we are not going into that much depth, because the thing which I want to have you with me in this course is more the top-down intuition about what these LSTMs are doing. So it means that at this kind of for this kind of course, we are not going to dig deeper into the mathematics of these cells. That can easily become 1/3 of a course like this one, if we want to dive into these details. So I hope you can accept that we're just going to look at it from a top-down way, so that you have a feeling of what these cells are doing, and that they do actually allow us to build up long-term correlations. Okay. I went a little bit over time, so let us take a small break, and then we'll be back in 15 minutes. And we continue with these topics till we come to autoencoders. And we are going to look at more code. So today is going to be a slide day, essentially. So just to remind you of some of the problems with the standard simple RNN, is that it can sometimes be very difficult to train and to get the proper long-range correlations or long-term correlations. So each of these LSTM cells contains a memory cell and 3 gates, as we said. And this forget gate chooses which information to erase from the previous cell state. And the input gate decides which new information to add to the cell state. And then we have the output gate, which controls which part of the cell state becomes the new output. And then the cell state update is given as a combination of this input gate and the forget gate. And the typical core LSTM equations, which we need to have encoded, are the ways we set up the information into the forget gate, the input gate, and then the way we change the cell state. And then we have the output, which is then given by the previous input plus this H0, now this bias, and this produces then a final output, which is then given by the what's the name of it? The dot product with a tanh H containing the new memory state multiplied with the results from the output gate. So the kind of intuition then, which we can have with us, is that the forget gates acts as a kind of soft erase signal. So FT close to 0 forgets, FT close to 1 retains the previous memory. And then we have the input gate, which scales how much the new candidate memory CT, or how much is written to that. And then the output gate determines how much of the cell's memory flows into the hidden state H of T, which is then transferred to the next cell. And by controlling these gates, the LSTMs, they try to keep long-term information when needed. And the basic layout is, as we discussed now, is then this forget gate, which we have here, which also changes the state of the previous memory gate. And then we have the input gate. And some of these are just grinded through a standard sigmoid or tanh. And then we have a so-called output gate, which then feeds in to the next time step. So if you then think of the comparison with a standard RNN, so in the standard RNN, what we have now is simply a correlation between the previous recurrent node or unit with a new one, which then feeds into the next one, but there is no screening of long-term memory. So that means that these setups here often favor a short-term memory fit. So you can improve on that by this sliding window option, which we discussed before the break. That is one possibility, to build in long-term correlations. But what that often means is that a recurrent neural network can be much heavier to train. So if you look at these different slides, you could then say that you have the cell state at the previous time step, and then you produce a new cell state at the current time step, which is then fed into the next cell. And the activations which come from the previous, this guy here, this H of T minus 1, is the one which is meant to keep track of the short-term memory. So the C here is in a way the long-term memory, whereas the H's, which connects the previous recurrent unit, or cell in this case, is the one which keeps track of the short-term memory. And then through the different magics which take place here, you have a new output which links in to the next time step and keeps track of the short-term memory. And then you have the C, which then is meant to keep track of the long-term memory. And these are the type of operations which we typically do then. So we have element-wise multiplications and element-wise addition operators in here. And these are the type of gates. So this is the input gate. We have the forget gate here, and then we have the output gate here. And the standard choices is that the type of activation functions, and you see the weights and biases, which are then parameters you need to train, they are typically given by either sigmoids or tanh functions. So as I said, the forget gate controls which information is remembered and which is forgotten, and that can reset the cell state, as we discussed earlier. And you see then the parameters which you need to fit. So you have a bias for the forget gate. You have the link between the forget gate and the H's. And then you can also have some X's which are fed in here. So as in the previous case, you could have the input values at every time step. And that gives you an additional set of parameters. And then obviously you have the connections between the input gate and the forget gate, and the forget gate, input gate and the output gate. So I'm just going to quickly go through this. You can see the type of input nodes you have to the gates here, and how they give you a set of parameters which need to be trained. So as I said, the input gate consists of both a sigmoid function, which decides what percentage of the input will be stored in the long-term memory, and a tanh function, which decides what is the full memory that can be stored in the long-term memory. And when these results are calculated and multiplied together, it is added to the cell states or stored in the long-term memory. And these are the typical operations with either a sigmoid or a tanh function. And then if you then look at the kind of short-term, short summary, brief summary. So you have the forget gate, the input gate, and the input gate here. And that gives you the new updated long-term memory. And the forget and input gate together also update the cell state with the following equation, which you see here. So we are not going to go through the mathematical meaning of these gates, just simply state what are the standard components of an LSTM gate. So I'm just going to scroll down here. And I wanted to show you a typical way by which you could set this up using Keras. And you can see in this particular case, I have a very simple data set, and I have an LSTM, and this is the way you would actually set it up. And you would specify the type of optimizers and this type of mean squared error. So the whole thing here is that, which I wanted to show you a little bit below here, is also how you can implement this to different applications. So one of the typical applications, and the application you will see below here, is an application to a ordinary differential equation, where we use the Runge-Kutta 4-4 method to generate the data. And then we are going to use an RNN to take the data from the ODE solver and then train a network which reproduces the training data and then can be used to make a prediction. So classical examples of the applications of these different methods, either simple RNN, but more popularly an LSTM. This is much more common to be used because the simple RNNs can be heavy to train. And you will see that if you run the examples in the lecture notes, you will see that the standard simple RNN takes a lot of time to train, even for simpler cases. So the LSTM has also fewer operations, and it's easier to train, or rather it takes less time. And it's the kind of standard choice also because you want to ensure that you have a proper reproduction of the long-term memory path. And these methods often speed up predictions compared to full numerical simulations. Obviously, if your numerical simulator is fast, then most likely there is no need to use an RNN. Most likely. Then you would just use your fantastic ordinary differential solver or partial differential solver and just stay with that. But if this is something which takes a lot of time, then you should consider using these methods to extrapolate beyond the training data. Biological sequences, they are effectively categorical time series. And I know that some of you are actually dealing with that for project number 3. And I think this is a very nice test case for what some of you are doing already with the data sets you have. So they typically capture long-range dependencies. They're widely used in genomics. If you are interested in going into that direction, and they handle variable length input by processing one element at a time. So there are some training tips which are often convenient. So pre-processed time series, normalized features. The sliding windows is a type of pre-processing. You can handle variable lengths of your data. Padding, for instance, if you're doing with classification of images. You should experiment with network depth, hidden units, and regularization to avoid overfitting. Consider bidirectional LSTMs or stacking multiple LSTM layers for complex patterns. This gated recurrent units is also simpler gated RNN that combines forget input gates into one update gate. That's another option to the LSTM, which we haven't discussed. And then you would typically monitor gradients during training, and you would use gradient clipping to stabilize learning if needed. So these are the kind of typical tips which you would use. And if you want to read more, I mean, there are some references here which I recommend. As I said, the GRUs often have a simpler architecture than LSTMs, and they are easy to train. So the gated recurrent units, which we haven't discussed. I wanted to say a little bit about the codes here. So there is an implementation on the MNIST data, if you're interested in using that. So as an example in Project 3. So people have actually taken this kind of data and they've looked at standard neural networks, and you will see that they really struggle with the data. And then you have the convolution neural networks. You would make a comparison with a CNN and a standard neural network. And then you can add on top of that a recurrent neural network, or as you will see later in the notes, there is an example of the MNIST data for autoencoders. So then you could test different methods and make an assessment of which one of them does the best job on the type of data which you have. And you don't need to use the MNIST data. You can use other images if you want to. So the examples here are examples which, if you want to use them, but they are, in this specific case, we actually using an LSTM, but in the example below, I deliberately actually implemented a simple RNN just to show how slow it is. Actually, I'm not going to run the code now because it would take 10 minutes for a simple case. But then you can look at the quality of the results. So this is a LSTM where we now do the standard training of the data. You've seen this before. We reshape the data. We have the 28 times 28 pixels. We normalize it. So this is something you should always think of to normalize the data. And in this particular case, we are then setting up a LSTM with 128 cells. So this is LSTM units, which you see here. So this is a parameter. And then you have the input shape, which is your image, which is a 28 times 28. And then the output in this specific case is an output which is then governed by the softmax function. So if you use the MNIST data, then you know that you have 10 classes you want to predict, the 100 numbers from 0 to 9. And that's why we then have activation function, the softmax, and then we have a dense layer, the final one, which is then simply a 10 class output. And you see again, we define the loss function, we have an optimizer, and the metrics which we want to deal with is the accuracy. So using TensorFlow or PyTorch makes it pretty easy to actually run these calculations. So feel free to use these examples in project number 3. And the thing which is nice here, you can see the number of parameters. I always like this option here, model summary. And then I do the training of the model. You specify the batch sizes, the number of epochs. I took some fewer epochs here, simply because I wanted to finish in time, because it takes time to run such a simulation. And I also, during the lab sessions, we have recommended always to use, if you're running heavy calculations, to get an account on the machine learning nodes at the University of Oslo, because there you have access to NVIDIA GPU cards. And both TensorFlow and PyTorch can be set up to run on GPUs. So as a UIO registered user with your email address, your account, you can then ask for access to the machine learning nodes. Just search online ML nodes UIO. And then you apply for access. So many of you have already done that. Okay, so try that, because if you, in project 3, if you end up running with pretty heavy data sets, and you will then typically see that your laptop is just going on and on and on and on. So then you have the possibility of running on better infrastructure. And this is for free. So when I use on the national resources, I pay 5.60 kroner per GPU hour. And some of the calculations which I run last year used 100,000 GPU hours, and that becomes expensive. So in this case, this is for free. So if you want to test it, please do try it. But you can see here the typical results, and it gives me an accuracy, a test accuracy on the MNIST data, which is 98%, which is roughly the human accuracy. So this very simple setup with 128 LSTMs did a pretty good job on the MNIST data. So give it a try. So I won't discuss the PyTorch. I just put up a PyTorch code, which is pretty similar to that. And it has much of the same setup, and you will recognize much of the same. It just changes a little bit the way you call it. So here you have an RNN LSTM. You need to set up the input size, the hidden size, and then the final one for the type of classes which you're dealing with. And you will recognize many of the same things here. Adam optimizers, specify the learning rate, the cross entropy, etc., etc. So what I wanted to spend some time on now is something which is closer to the kind of research which I'm doing and the things which I'm interested in. This is solving differential equations. So are you all familiar with the Runge-Kutta method? So this could be an example of a problem which you could actually implement in project number 3. So if somebody is interested, I could design that for you as an alternative to the partial differential equation solver. So what we are doing here, we are taking a Runge-Kutta method to 4-folder, and we are solving a differential equation, which is a harmonic oscillator, but with an external force, which is applied to the system. This is what we discussed last week. And then we have a damping term. So let me just remind you quickly of what we did last week, because I used last week a differential equation to motivate the recurrent neural networks. So let's just take a look at the differential equation, which we are going to simulate. So in the equations which you will see and which you have access to through the Jupyter Notebook this week, we are simulating this equation here, which many of you probably have seen. And then there is some kind of noise here with a damping factor, dx dt. And since this is a harmonic oscillator, we have a time dependence here. And then there is an external force, which is applied to the system. And what you will typically see, if you don't have, if this f of t is equal to 0, what you would see then, suppose now you're looking at, as a function of time, you're looking at the position x. And then you may remember from courses in mathematics or physics, for those of you who have studied this type of equations, is that the equation will oscillate. But since you have this damping factor, it dies out. So you can have critical damping, you can have under damping, and you can have over damping. Does that ring a bell among some of you who've taken a course in mechanics? So a typical situation you will see, due to the fact that you have this damping factor, so this is a kind of friction, is that your motion will look like something like this. It will oscillate. So this is normally what we call under damping. In critical damping, what you will see then, and that depends on the parameters which you have. In a critical damping, you may just go down quickly down to 0. Now, if you add this external force here, if you do that, then you may see some kind of damping where the system, these equations, the first part is going to damp the system due to the friction, but then the external force kicks in, and that external force can then make the system just oscillate regularly. So it could go down like this, but then suddenly it puts everything into regular oscillations, and life is just deadly boring for the rest of your time. So the system tries in the beginning, depending on your initial conditions, your damping term, it tries to change the motion, but then the external force kicks in, and that's the one which defines how the system develops over time. So this all depends on the parameters which you see in front of the force, the damping factor, the mass of the particle, etc. So this is essentially the type of equation which we are going to solve. by using a standard solver, which is called the Runge-Kutta method to fourth order. This is a kind of basic kitchen ingredient in essentially all ordinary differential equation solvers. It does not conserve energy, however. That's one of the drawbacks with these methods. So if you need to conserve energy, you need to think of other methods like the velocity-Valais method. But that's another discussion. So let's go back to the equation or the Runge-Kutta code. So you will see here that we have the RK4 method, which sets up the different contributions to the solution of the differential equation. We set a time step delta t, discretize, a final time, and then we have the initial positions and velocities. And then we define these parameters in front of the force, and then we simply solve it. And this is what it looks like. So in the beginning, the initial conditions and the damping try to decide, say a little bit more, but then the system has been taken over by the external force. And you will see that if I now let this be 200, you will see that quickly here if I rerun it. You see now the initial conditions and the damping are trying to set the scene, but then the applied external force forces everything to oscillate in a pretty boring way. Okay, so this is the data which we're going to train with. And then we are going to set up a recurrent neural network. And this simply runs that code, which you saw now, and you can play around with it if you want to. I'm now in the example which you see here. I do not train on velocity and position. I only train on position. But there's nothing which hinders you to train on both velocities and positions. So I just try to simplify it. And I also made a simple recurrent neural network. So this simply takes my Runge-Kutta method and it sets up my data. So this is essentially me setting up, it plots the data, as you can see here. It sets up max time. It also normalizes the data. So this is something you should always think of doing. So this is a normalization of the data. And also made two models. One model, where I'm simply making an input length equal to 1. So this is my sequence length. So here, I do a step at a time. And then I made another model where I actually have the sequence length equal to 10, so I have a sliding window. So in this case here, I just have xt, which feeds into t plus 1. So this is defined here. So coming back to this discussion we had on how you make the fit. So that becomes a hyperparameter. So I have just a one step at a time, and I don't mix like I had in the example before the break where I had the sequence length equal to 3. I could have a first window with x1, x2, x3. The second window had x2, x3, x4, etc. So now just to see what happens, because you don't know a priori which one is the best option. And then I'm doing the same standard test size equal to 20%. I set up my data, train, test, split. Pretty familiar with that now. So sometimes I use the standard scikit-learn, other times I just leave it out. And now I build a simple model. So I have my input shape, and then I have my simple RNN. I define the hidden size here, and the hidden size is then set to 32 and 64. So it means I have 32 recurrent nodes and 64 recurrent nodes. And as you can see now, my simple output, I just have one output. I have activation function, a tanh. I have my Adam optimizer. The mean squared error is my metrics. And I'm optimizing the mean squared error without any hyperparameters. So this is pretty straightforward to set up with me giving it the training data. Does that sound reasonable? So it shouldn't be that difficult to actually use these libraries, and you will find a similar example with PyTorch. I think I still have a bug in the PyTorch code, actually. This is why the lecture notes this morning were a little bit late, because there's still a bug in the PyTorch code. And I have to find it out. So if somebody finds it before me, let me know. And so I'm not going to go through here, because you see now that when I've done the training, I'm simply just printing out the results. And this was the training data which I had. This is the trajectory which I want to replicate. The model here has the different models have actually different number of parameters. And this is again the nice thing which I like with the TensorFlow, it is model summary. And you can see the training here, and the loss function is, so it's actually doing pretty well. And you would see then that if we go down here, model A and model B show actually a pretty good, actually the model A, which had a sequence length of 1, is actually doing a better job than model B, which had a sequence length of, what was it now, 20? Yeah, I don't remember. So in this specific case, you would actually opt for this model here, which was even simpler. And you can see now the loss function is, as you can see from here, the loss function is basically very, very small. So that was model B, and model 1 gave a loss function which is a similar value of 10 to the minus 7. So this is a typical example on how you would use, and you can see the model A prediction, which and the true one, they are basically overlapping here. So this is a typical example on how you would use a recurrent neural network, and it's pretty easy if you look at the way we have set up the machinery to go back here and simply replace what I put in here as a simple RNN. You could then simply replace that one with an LSTM. So if you want to use a long short-term memory and play around with it, that's the only change which you need to do in these implementations here. Any questions? Yeah. Oh yeah, absolutely, absolutely. So that's the, so as I said, I mean, your recurrent unit doesn't need to be a standard neural network. It can be a CNN. Absolutely. Okay, so I'm going to stop here a little bit with these methods. So there is a PyTorch example, but I wanted to say something about autoencoders. So that's going to be the final topic this semester. And these autoencoders are very powerful methods. And the way you can think of them, if you want to get a kind of a feeling of what they do, is that you can think of them as a way to reduce the dimensionality of a problem. And you're going to find a latent space, which then encodes the essential information. So let me show you in a graphical way first what these autoencoders are doing. So there's a lot of text here, but let's try to give you guys a kind of intuition about what an autoencoder is. So this is going to be our final topic. And if we now look at autoencoders, so what we want to do is the following. We want to find a latent space which you can think of as a space of reduced dimensionality compared to the full space of degrees of freedom you have. This latent space is meant to represent the most important degrees of freedom. So suppose now you have 1,000 features in your input, and you're asking yourself, which one of these features are the most important one to describe my data? There is a method which we are going to link with, which is called principal component analysis. I'm going to say a little bit about that next week. which is a way to reduce the dimensionality of the problem by diagonalizing the correlation matrix. And you keep only those features which have the largest variance, which is again the same as the largest eigenvalues of the correlation matrix. So suppose now that you have 1,000 features, and it's only 10 of them. When you add them up, which give you, let's say, 98% of the total variance. Then you will say that these 10 features are the most essential ones. And I'm going to train a model using only these essential features. I leave out all the other ones because they are insignificant. So as an example, we discussed housing prices. So most likely the color of the house doesn't influence very much the price of the house. Does that sounds reasonable, right? Because most people will repaint the house. That's most likely. So when you are then setting up a model for house prices, the color of the house is something which you would neglect in making a model. You would typically look at the number of bathrooms, the size of the house, the year it was constructed, the number of rooms, etc. Because these are typical parameters you would expect to be more important. So if somebody gives you a list of 30, 40 features for the house price, you would probably single out, let's say, only 5 to 10 of them. And you can do this in a systematic way by principal component analysis or using decoders or autoencoders, as we call them. So let me just show you the basic setup of an autoencoder. So think of you having some input, and let's just call this input for Y0 and Y1. So you have a set of input data, and n minus 1 here. Now, this data, we can represent that by different nodes or units. This data feeds in to what we are going to call an encoder. This could be a standard neural network, and you're encoding the data into that one. So you want to make a model which reproduces your data. So it means that there are some hidden layers, and let's just call this for H0, H1, and this goes all the way up to H of M minus 1. So that you don't need to have the same number of nodes. Now, these are obviously connected. So this feeds into that one, etc., into all the other ones. And now, since I have many colors, I can play around a little bit with colors as well, etc. So they feed in here. Now, this part here, this encoding part, is then feeding in to something which we are going to call a latent space, or latent feature representation. And this is important. It's a much smaller space than the encoder has. So I'm just writing this as a much smaller space. So I have some effective degrees of freedom, which I'm going to put into this latent space as the essential ones. So when we are going to look at the link with what we call a principal component analysis, there's actually between autoencoders and the principal component analysis, there is a one-to-one connection if we have a linear transformation. And I will show you what that means. Now, these data sets which you have here, these latent features, are then used to reconstruct something which is called a decoder. So this latent features feeds then in to a decoder part. And that can contain a new set of nodes, which I label with a variable g, g1, and this goes down to some gl minus 1. And finally, this one is then fed into the final model part, and this is called the output. So let me just mark this properly. This is the output part, the decoder part. These are the latent features, the encoder part, and the input. And this output is something I will label with a Y0 tilde, Y1 tilde, etc., down to yn minus 1 tilde. So what we are doing with the decoder is that we are reconstructing the output. But normally the decoder can have smaller dimensionality, or it can have the same dimensionality as the encoder. Now, when you do a singular value decomposition, this has been the standard way to reduce the dimensionality of an image. So if you have a 100 by 100 matrix and you perform a singular value decomposition, you can actually use only 5 of the eigenvectors, which correspond to the largest eigenvalues. And you can use these 5 eigenvectors to represent the image. Now, since you have performed a singular value decomposition, you know all the eigenvectors. That means that you have all the information about the latent features. And you can use the eigenvectors to reconstruct the full image. So that means that if you think of the singular value decomposition, I would take my features. My encoder is the SVD. My SVD reduces the image to a smaller one with respect to the way we represent it. So instead of 100 singular value vectors, I could use 5. But these 5 are connected with the SVD here, because I can then decode it and get back the same image. So I would just store the information about the SVD and compress the image to a smaller one. And then if needed, I can reconstruct it because I have the SVD, which is my encoder and decoder. So I know that not everybody is fully familiar with that. We are going to repeat some of these things next week. But now I wanted to just set up the basic machinery of an autoencoder, because what we want to do is to optimize a metric for success. So we're going to have a function h, the decoder, which is going to be given by some weight or some variable, which we want to optimize. We are going to have this function y, the output, which is going to be a function of this decoder. So this is the encoder, and this is the decoder. And this g of v, so we have new parameters. And then we want to optimize, if we define a metric like the mean squared error, we want to optimize the difference between y of I minus y of I tilde squared. It means that the optimization, in our case, is going to look like this. And this is probably the last thing we do today. So the optimal parameters, v and w, are again given by the minimization of v and w of 1 over n of I equals 0 to n minus 1 of y of I minus y of I tilde squared. And then we can make, if we now suppose that we have a linear model in these unknown quantities, this is the simplest possible model we can make. An autoencoder, since the decoder and the encoders can be neural networks, it is normally never given by a linear dependence. But I could now set up a simpler argument. So suppose now that we have a linear model, then what I'm going to do then is simply to say that h is equal to this w times y, and g That's also something which is linear. So that means that y tilde is simply going to be given by v times w times y. Then what we are going to optimize is the following. Equal argmin of v and w of 1 divided by n, sum over I. And now I'm going to have 1 minus v times w times y squared. Now, what I will show next time is that this is the same as the simplest possible principal component analysis I can make. So that would be the lecture next week. And then we are going to look at some simple implementations of autoencoders. And after that, we're going to wrap up everything. But autoencoders is actually very, very simple to set up. And if you look at the examples, the typical case is that you have a neural network or even a convolutional neural network. There are examples on how we can use the MNIST data with an autoencoder. So the autoencoder, essentially what it is a way to reduce the dimensionality of the problem into a latent space. And then with this latent space, which then contains fewer degrees of freedom, we can reconstruct the output. So the whole thing with an autoencoder is to be able to find the relevant effective degrees of freedom, which captures most of the information you're looking after. And you can make a nice mathematical link with the principal component analysis. And this is what I will sketch to you next week in the first lecture. And then I will also show you some simple codes which you can set up with autoencoders. And this is also in the lecture notes today, but you will probably see then. So let's just try to wrap up a little bit. Just give me one small minute, and then we are done. So the basic structure which you will see is something like this. You have an input, you have the encoder, you have some latent feature which then effectively finds the right degrees of freedom, and then you can reconstruct the input. So the quantity we are interested in is actually to find this latent space. So the below here, you will find some simple examples on how to do that with an autoencoder. And when you use TensorFlow, this is actually pretty easy to set up. So you have an encoder part and a decoder part, but we will discuss this in more detail next week. And the other thing which we will do then is to say a little bit about the link with the principal component analysis, which is the last lecture. So as I say here, stay tuned. This series of lectures ends next week, unfortunately. So, and the autoencoders are meant as a kind of teaser for more deep learning methods. For those of you who actually want to study in more depth what these methods are actually doing and why they are so interesting as universal approximators. Take a break. Is that okay with everybody? Okay.